spent the first phase of this series building brilliant AI brains, agents that can reason, plan, and retrieve vast amounts of historical data. But a brilliant brain locked in a room still cannot affect the real world. To do that, the system has to pick up a tool. In our last episode, agent number 6 demonstrated how to synthesize the world's published scientific knowledge. But even that advanced system was trapped within text generation. It could tell you the molecular sequence of a protein, but it could not trigger the centrifuge to actually test it. Agent number 7 is the tool-using agent. It is the foundational architectural pattern that allows a language model to invoke external functions, hit an API, run a database query, or modify a local file. This agent marks the beginning of the tools and orchestration tier. We are moving out of the strictly cognitive layers and into physical and digital execution. This is where the model stops merely discussing a problem and gains the hands required to manipulate its environment directly. Crossing the threshold from cognition to action is the mandatory bridge. It transforms the AI from a conversational oracle into a functional system component. By default, a large language model operates in a closed loop. Text goes in and text comes out. Give an LLM a prompt like, "Show me the trend of our ad clicks over time," and it immediately hits a wall. The model can easily generate the Python code required to aggregate the data and configure the axes of a chart, but it cannot inherently run that code or render a PNG file directly to the user's screen. A common early attempt to solve this is to naively wire the language model directly to an external API, allowing it to trigger code execution automatically. The problem is that APIs require exact deterministic parameters, and network connections occasionally time out. When the model guesses an argument, say passing campaign ID instead of the strictly required campaign name string, the API rejects the call. Without a safety buffer, a single transient error or slight hallucination from the LLM crashes the entire application. The solution to this fragility is a decoupled think, plan, act architecture. This diagram shows the 6-stage loop that strictly separates the AI's decision-making process from the actual physical execution of the task. The user goal flows into the reasoning core. The system parses the user's intent and formulates a plan, completely isolated from any external systems. Isolating the think phase from the act phase creates a critical safety layer. The model evaluates what needs to be done before a single line of execution code is triggered. The reasoning core consults the tool registry, a precise catalog defining authorized actions. This registry holds explicit schema contracts like JSON schema. It dictates require inputs, forcing the agent to align its plan with the software it wants to use. By forcing the language model to plan strictly against these known contracts, the registry and reasoning core work together to prevent hallucinated API calls from ever firing. This decoupled structure works flawlessly for a handful of tools. But what happens to the agent's accuracy when the registry grows from 5 tools to 50 or even hundreds? You hit what engineers call the 14% cliff. Give an agent 50 tools, and its accuracy drops below 14%. The sheer volume of options overloads the model's context window. To solve this context overload, we implement a tool selection funnel. This is a 3-stage filtering process designed to progressively narrow the candidate list before the LLM makes a final choice. The top layers use broad intent classification and vector-based semantic search. This quickly eliminates 95% of irrelevant options, cutting 100 tools down to just 5 based on mathematical similarity. The final stage applies constraint filtering, verifying input types, permissions, and limits. This guarantees the remaining tool is viable. The funnel protects the AI from its own context limits. Rather than overwhelming the model with an entire hardware store, it hands the agent the exact tool it needs on a silver platter. With the optimal tool selected, the agent moves into the act phase, where it finally touches the real world. Here, the execution engine takes over. Acting as the system's foreman, it manages the current state, passes variables from one step to the next, and triggers the physical tool. But touching the real world is messy. Network calls time out, files get locked. Failure is an absolute inevitability. If an execution fails, the architecture must absorb the impact. Instead of crashing, the system catches the exception and routes it into a safe recovery loop. This is achieved through the guarded tool chest. Every single function is wrapped in defensive logic designed specifically to absorb runtime exceptions and enforce strict timeouts. The wrapper intercepts the error and feeds a clean failure message back to the reasoning core. The agent reads the error, adjusts its parameters, and dynamically replans the attempt. This infinite, guarded error handling loop separates a fragile Python script from a resilient, production-grade agentic system. We can see this exact logic applied in the codebase for our data visualization assistant. This is the Python implementation for the plot line chart tool. Notice how it is built as a single responsibility function. The parameters here, the data frame, xcall, and ycall, are the strict schema contracts. The reasoning core must fulfill these exact requirements before the function will run. Above the definition, a graceful fallback decorator wraps the execution. This is the physical, programmatic implementation of the guarded tool chest, ensuring that a malformed column name doesn't crash the server. A central orchestrator, the DataViz agent, loops through the think, plan, act cycle. It safely passes the data state from a CSV loader, through the aggregation tool, and finally directly into this chart renderer. This decoupled structure forms the universal pattern for safe AI action. It scales from generating a simple chart to triggering a massive database migration. Stepping out of the codebase, this architecture translates directly to complex enterprise environments. A tool using Agent can be engineered to safely manipulate almost any complex digital environment that has an accessible interface. That means securely executing complex SQL queries, automatically triaging and responding to internal IT tickets, or evaluating and pushing code deployments. However, this architecture has a built-in limit. Agent number 7 is incredibly capable, but it is still just one specialist, reaching for one tool at a time. A single craftsman with a toolbox is powerful, but solving complex, multi-stage business workflows requires an entire factory floor. The next step in our hierarchy is teaching these specialized hands to work together. Next time, we cover agent number 8, the chain of agents orchestrator, which takes this exact tool use pattern and coordinates it across a team of collaborating AI specialists. You can find the complete Python code, tool schemas, and wrappers for Agent 7 in the book, 30 Agents Every AI Engineer Must Build. Mastering individual tool invocation and error recovery is the mandatory prerequisite. Only when an agent can safely wield one tool can you begin building true, scalable, multi-agent intelligence.